Thank you for the invitation. It was very nice. So, as we said, we're going to talk about Plurisubharmonic geodesics in non-Archimedean geometry. If you do not know much about non-Archimedean geometry, do not worry. I'll spend a lot of time trying to explain what it is and to draw some parallels with complex geometry. So, I'm going to start off with some. Okay, this is not working. Okay, I'm going to start with some motivation. So the general idea is that non-Archimedean geometry encodes the behavior of asymptotic phenomena in complex geometry. So, for example, if you take a degeneration of complex manifolds over the punctured unit disk, you can realize it more or less canonically as a scheme over the field of complex Laurent series. The reason for this, well, it's mostly in the projective case, is that you can see it as a subvariety of projective space that is going to be finitely presented by homogeneous equations with coefficients in the functions in the ring of functions holomorphic on the punctured disk, which you can identify with Laurent series. That's one way to interpret kind of an asymptotic complex phenomenon using Archimedean tools. Another thing, so do not worry if you do not know what I'm talking about here. This is just some informal motivation, but this is not going to be important for what's coming later. So if you have a geodesic ray of PSH metrics or functions, you can canonically associate to it a non-Archimedean PSH metric on what we'll call the trivially valued analytification of the underlying variety. This is very nice, and it has had some very nice applications recently. For example, if you have a function always convex along PSH geodesic rays, this means that you can take the slope at infinity of your functional, and a functional that we're particularly interested in is the K energy, the Mabuchi energy, and there is a big conjecture that relates the asymptotic behavior of the K energy along geodesic rays and the existence of certain K metrics on the manifold. This is the YTD conjecture for Yotti and Donaldson. And recently, these tools have helped give a new proof of this YTD conjecture in the K-Einstein case by Berman, Buxom, Johnson around 2015. And recently, Chile has also made some real big progress on the more general case of the conjecture. And many other people as well I simply cannot cite because there are too many. And in the same direction in the study of the K-modular problems, constructing the moduli of K-polystable varieties. These Archimedean tools have proved very useful. Using this correspondence here can also be help to understand the way a volume form along a family of Calabi-Yau can degenerate, and this is something that has very strong applications to mirror symmetry. That's what they call the SYZ conjecture that can be formulated using an Archimedean terms. And I think Youngli recently made some good progress on this using the work of Buxom Johnson on hybrid spaces. And there's also some applications in Archimedean geometry. So I cannot really say I know anything about Archimedean geometry, but I know that they use a lot of non-Archimedean potential theory. So if you like Archimedean geometry, you'll be interested in what I have to say. So we will start by defining our very most basic object, which is an Archimedean field. So we will define an Archimedean field to be a field that has an absolute value, and we ask that it is complete with respect to the topology induced by its absolute value. And furthermore, we ask that this absolute value satisfies the ultrametric inequality here. So the absolute value of a sum of two elements is more than the maximum of their individual absolute values, which is something that refines the triangle inequality. And it's actually very strong. It makes a lot of things strange. Before going on to some examples, I'll just write something here, which is that if you have a complete valued field whose absolute value does not satisfy this ultrametric inequality, this is called the Geffen-Measure theorem. So I hope you can read this. So if this is Archimedean, then K is isomorphic to RQ, to RC, sorry. Any other complete field then has to be an Archimedean, a complete valued field. So for some examples of non-Archimedean fields, technically any field can be endowed with the trivial absolute value, which is Archimedean, non-Archimedean. Is defined simply by taking the absolute value of 0 to be 0, and the absolute value of any other element in your field is going to be 1. And so by the axioms of a field, by the very axioms of a field, any field can have this trivial absolute value. So it's technically Archimedean, but it doesn't really respect the structure of the field. A more interesting example are fields over on series. So just over any general field K of T. So I chose C. I chose the Laurent series over C and over FP because there are kind of canonical examples, and the absolute value is the usual t-adic absolute value of power series. And finally, perhaps of more interest to number theorists, you have the fields of p-adic numbers. So you have QP, and then you can take the completion of some closure, which we call the complex p-adics. So these are the objects that are going to be the basis of our geometry. And now, oh, I forgot to erase this. And now, so in complex geometry, if you have a complex projective variety, then it can be realized as a complex projective manifold by the JGA principle. And since we're going to want to do analytic geometry over varieties on Archimedean fields, we need a notion of an analytic space associated to such a variety. So to a variety over an Archimedean field K, we're going to canonically associate its Berkovich analytification. So this is something that we're going to describe in some simple cases. So in the affine case, if X is the spectrum of an algebra of finite type over some Archimedean field, then you can realize the Berkovich analytification as the set of multiplicative semi-norms on your algebra. So there are algebra semi-norms that are bounded by the usual absolute value on your Archimedean field. And you endow this with the topology of pointwise convergence. A nicer way to see what happens in a case that's very important to complex geometry, if you take a complex variety X and you take its Berkovich analytification with respect to the trivial absolute value that I talked about, then the space Xn here is going to be realized as the space or a set of valuations on function fields of subvarieties of X that restrict to trivial valuation C. So simply you take take Y as a variety of X, and then the space of points of Xn are going to be things of the form nu from C of Y to R. And they restrict to the trivial valuation. Okay, so implicitly here I have used the correspondence between valuations and absolute values. So if you have an absolute value and you take minus log of it, it's a valuation. And in the other direction, if you take the exponential of minus valuation, then you get an absolute value. This is a kind of dual point of view that we have to keep in mind sometimes. And so there are many ways to realize a GAGA principle for non-Archimedean varieties. We kind of like the Berkovich analytification because it preserves some rather fundamental topological properties, such as compactness, connectedness, and Hausdorffness, which are really the bare minimum you should ask for. And finally, to show that this is not just a random construction, so we can also analytify with respect to any absolute value. So we can analytify with respect to an Archimedean absolute value. And if we have a complex variety and we take the analytification with respect to the usual Archimedean absolute value of C, then we obtain the analytification of a complex variety in the sense that we all know. So in short, this means that it all works just as we want. Now we're going to turn to prime potential theory. So usual setup is that we're going to take X to be a complex projective manifold and L to be an ample-line bundle on X. And the main object of prime potential theory is the space of Plurisubharmonic metrics on L. And these objects we're going to define as a decreasing limit of some smooth metrics that have positive curvature form. So you might immediately be thinking, why is this definition, and why do we use this definition? So this is equal to the or equivalent to the usual definition of PSH metric is from the work of Bloch-Ecologier and de Maillet. So this is very much not the usual definition, but this is the one that will be the easiest for us to copy into the non-Archimedean world. So now in Archimedean world, we have a projective variety over an Archimedean field K. And we again take an ample-line bundle on X. By factoriality, we have a morphism between their identifications. And now we want to define a notion of a Plurisubharmonic metric on L. The problem is that we do not really have any differential calculus or anything on Berkovich spaces. So we need to work completely globally, if possible. So we are going to try to take this definition to define a sort of good class of metrics that are going to correspond to some very nice metrics also in complex geometry. And we're going to take their decreasing limits, and we're going to define this to be a Plurisubharmonic metric, but an Archimedean. So we start by saying this thing. So if you take S a section of L or of some power of L, it gives a singular metric log of S on the analytification of L on L. So in the trivially valued case, it's a bit explicit. So we recall that in the trivially valued case, the points of Xn correspond to evaluations on some function fields of subvarieties of X. So in particular, you can take a local equation for a section S and simply evaluate it. It's basically an order of vanishing, and this is so this gives the potential of the metric. And in trivial valued case, a metric is basically a function. There's a canonical way to transform them into those. So what we do now, just a little remark here, is that I use the additive notation for line bundles. So if you're not familiar with this, ML means the mth tensor power of L. We can take L plus M to be L tensor power of M. The inverse is going to be A minus, and also the tensor power of a metric is going to be denoted additively. This is just we just prefer to work additively, but you can transform this in your mind if you want. And so we're going to take a maximum of singular metrics of this type obtained from a base point free basis sections of the mth tensor power of L itself, with some very important constants that are just going to be real or rational. The rational case is a bit nicer because it has a geometric interpretation as test configurations or models, but you can also just define real Fibonacci metrics with real coefficients here. So we define this to be a Fibonacci metric on the analytification of your line bundle. And this is not very far from what we define to be a Fibonacci metric in the complex case. So in this case, it's just the log of the sum of squares of your matrix. And it's in fact, it's even closer than you think, because if you take the power 1 over t of this, and then you take, you take the power t here and the 1 over t down. So essentially, just the LP norm of the sum. This converges to this as t goes to infinity. This is simply the convergence of the LP norms to infinity, and you can view this as an example of an Archimedean limit. And so, as I said before, we will then define a Plurisubharmonic metric, an Archimedean space, but this also works in the complex case, to be a decreasing limit of Fibonacci metrics. So it has to be a net rather than a sequence, but in the continuous case, we can reduce to sequences. If this is something that bothers you, you can just picture a sequence in your mind. It's just a technical thing that we have to use. Oops. And so there is a very nice characterization of the class of PSH metrics, originally from the Maillet in the complex case, and from Buxom-Favre and Johnson in the non-Archimedean case. So the set of the Plurisubharmonic metrics can be realized as the smallest set that contains all Fibonacci metrics, that is stable under adding some constants to your metrics. This is stable closed under taking finite maxima, and also under taking decreasing limits. So this is yet another clue that our definition is correct, because this is something that really characterizes them in the complex case, and it turns out to also characterize them in our case as well. And so, given d plus 1 upple of non-Archimedean continuous PSH metrics, or Fibonacci metrics if you prefer, there is a way to define Monge-Ampère measures. So the DDC phi0 times DDC phi1, etc. There are two ways to do this. There is the approach of Chamberlain and Ducrot. So you show that there exist local tropicalizations of your Berkovich space, and then you pull back the differential superforms of Lagerberg to your space. And the other approach is via intersection theory that's originally developed by Gubler and then many other people. But all this is simply technical things that doesn't really matter for the rest of this talk, but yeah, what's important is that it works. But I put this for as a cultural thing. now we're going to define a quantity that's going to be very fundamental for us. And I mean to emphasize that due to the machinery we have developed so far, we can proceed exactly in the same way in the complex and in the non-Archimedean case. So we take two Fubini 2D or continuous PSH metrics phi0 and phi1, and we define the relative energy to be this normalizing constant times the sum of the integral of your difference of metrics along their iterated Monge-Ampère measures in a certain sense. And so this is something that might look a bit awful right now, but it's simply a higher dimensional analog of the of the usual energy from classical potential theory. And it's something that's important because you can realize it in the complex and Archimedean case as the primitive of the Monge-Ampère operator, in the sense that if you take the derivative at t equals 0 of a convex combination, this is really just a sort of a reference or control metric, but it doesn't matter. And another metric here, this is equal to, so this is not going to matter at all because we're going to find the integral on xn of phi prime minus phi against the Monge-Ampère measure of phi. Okay. So this is a primitive in that sense. The Monge-Ampère measure is the DDC phi to the maximal power. And so, this is going to allow us to define what we'll call the finite energy spaces. So this is very classic in the complex case, but this is sort of new in the Archimedean case. So we're going to fix a metric, a reference metric that is going to be continuous on L, and then the assignment to a metric phi of the energy of phi with respect to phi ref is going to define a functional on the space of continuous PSH metrics. And we can extend it to the space of PSH metrics in general. So this energy is going to be monotone. So if we take a decreasing approximation of this in PSHL, and this is going to be in let's say, okay, I say Fs of L. Then this the limit of the energies of your sequence of your net of metrics is going to be well defined. Well, it can be minus infinity, but it makes sense at least to take this limit. And now we can define simply the space of finite energy metrics as the space of those PSH metrics that have finite energy. So you might wonder whether the choice of a reference here matters, and it does not, because if you are willing to do the computations in this horrible expression right there, you're going to see that if you take another reference metric phi2, then the energy of phi0 with respect to phi1 is going to be equal to the energy of phi0 with respect to phi2 plus the energy of phi2 with respect to phi1, which means essentially that it's not going to change whether or not the energy of phi0 or phi2 is finite, because this is always going to be finite if both metrics are continuous. So this space is in fact independent of the choice of a reference metric. But we have to deal with these reference metrics anyway, in the especially in the Archimedean case, where sometimes we just do not have a canonical metric to use. Now I'm just going to briefly review some history about the defining metric structures and geodesics the space of PSH metrics or some subclasses thereof. Oops. So first, so Mabuchi in the 80s managed to find that you can put a Riemannian, so infinite-dimensional Riemannian manifold structure on the space of smooth PSH metrics, which can be seen as a kind of a D2 type metric. Then Sam and Dalton in the 90s realized that the geodesic equation for D2 sort of corresponded to solving a complex Legendre equation. And I'm going to jump ahead a couple years. Chen in 2000 proved that in fact there exists complex geodesics in this space, but they weren't smooth for all time. This was a question that was asked whether if you provided you had a geodesic, you could have some natural regularity. And Chen showed that they have they're not smooth for all time, but they have a C11 regularity, which is a boundedness condition and the mixed secondary derivatives. And I'm jumping ahead even more by at least a decade here. There's a lot of important history in between, but not for this talk at least. But Darvash showed that you can define some finite energy spaces, in particular A1, but also the EP spaces. Those spaces are metric complete spaces, and they're also geodesic. And so here, in our case, we are going to focus on the D1 case, which we'll find is very related to the Legendre energy. So first, we're going to have to define our distance. So we take two finite energy metrics, phi0, phi1. In the complex case, this to emphasize that this is the complex case. And we're going to first define the so-called rooftop envelope of the two metrics, which is the largest PSH metric that is bounded by both phi0 and phi1 above. So you can imagine in the case of convex functions. So a convex function is basically a PSH function, right? So you have these two convex functions, and then your envelope is going to be something like this, roughly. Oopsie. Okay, that was not very precise. So you will excuse my poor artist skills here, but so this would be the envelope of F and G. So this would be the convex envelope, and you have to imagine the same, but for PSH functions or metrics. And so we are going to use this envelope to define our distance. So we take the distance between our two metrics to be the sum of two energies. The energy of phi0 and phi1 with respect to their rooftop envelope. So you might wonder, we haven't talked about positivity properties of the energy, but if you remember, we had that the energy of two metrics is constant times the sum of the integrals of the difference of your metrics against some positive measure. And so immediately, if phi is bigger than phi prime, this implies that the energy of phi prime is positive. And by the very definition of the envelope, this metric is bigger than this metric. So both terms here are positive or non-negative if you have some different conventions what you call positive and negative. Okay. And so what's rather striking is that this works exactly the same in the non-Archimedean case. So it was first proven in the trivially valued case and then generalized to almost arbitrary non-Archimedean field. There is a technical hypothesis that we will review later on related to these envelopes. So we can again define the envelope of two PSH finite energy non-Archimedean metrics to be the maximal PSH metric bounded by both of them. And we can define exactly the same way our distance on the space of finite energy metrics, and it turns out to actually be a distance, which is very nice. Now, we turn to the problem of geodesics. So in the complex case, you can take what we call the Perron-Weimermann envelope, for example, of all PSH segments joining phi 0 and phi 1. And so what we call PSH segment here is going to be a PSH metric on the product of X with some annulus that's going to represent the segment 0, 1. And we ask that is S1 invariant. So if we draw a picture very roughly of, so this is S1. We can take a small annulus within. It's not very balanced, but let's just pretend like it is. This is Z equals, I believe, 1/E. We're going to look at functions defined over this annulus here. We're going to call A. And a function that is defined on A and is invariant under rotation can be canonically identified with a function on any segment here, in particular 0, 1, by setting t to be minus log of z, which you'll see makes it so that t is between 0 and 1 as you go toward the center. And so we define a PSH segment to be something that is a PSH metric on a product of this annulus with X and S1 invariant. And the PSH condition is essentially going to translate into being convex in this variable t. And so you take this kind of envelope of all segments joining our two boundary metrics or two endpoint metrics. And this is going to be a geodesic for D1. And in fact, this is going to be a geodesic for all the DP distances. In the D1 case, it is not the unique geodesic, although it is sort of distinguished. And so for regularity issues, as we mentioned before, if the endpoints are smooth, then our geodesic is going to be C11 at best. And if the endpoints are simply a finite energy, then they are going to still have finite energy for all. The geodesic is going to have finite energy for all time. Now we want some similar results, so we want to construct a geodesic like this. We want to show that they are D1, and we want to have some to study some regularity questions. Now the main problem is that we did not really have a notion of smoothness for our non-Archimedean metrics. So the best thing we can hope for is continuity, because it doesn't really make sense to consider a smooth metric on Archimedean analytic spaces. So we're first going to define what we call PSH segments. So the problem is that unlike in the complex case, we do not really have a good way to define PSH functions on products of analytic spaces. It's a bit complicated, so we kind of have to have a define our things by hand. So we just take it before is a base 0.3 basis of some power of L, and we define a Fibonacci segment to be something that 2t. I think I must. T is in 0, 1. This maps to this phi t, which is as before the singular metric, which is going to be balanced by some convex combination of pairs of numbers this time. If you fix a point x, so this is the only part that depends on your space. So if you fix x, this is t of phi t of x is simply going to be a convex piecewise linear function. So this would be 0, this would be 1. And as I said, this maximum is always going to be finite if your basis is base 0.3, which is a very important point. And so as before, we are going to define a PSH segment to be a decreasing limit of a sequence or of a net of Fibonacci segments. And we can prove that just as in the case of PSH metrics, it is the smallest class of segments in a certain sense that contain all Fibonacci segments that are stable under finite maxima, under adding constants, and under taking decreasing limits. And in fact, in the complex case, since we have defined our segments technically as PSH metrics, this basically follows from the fact that this is true for PSH metrics in general, as we mentioned before. Oops. So now our main result here is the following. So if you take two finite energy metrics in the non-Archimedean case, then there exists a maximal segment which is obtained as before as the maximal envelope of all PSH segments joining the endpoints. And this maximal segment is also a geodesic for the D1 distance. And for so we have the E1 regularity because I did not mention it here. I should probably mention it, but phi t is in E1 for all t. And if the endpoints are continuous, then our geodesic is also going to be continuous in time and in space, which is again as best as we can hope for, really, because we do not have smoothness or anything. So there is something that I swept under the rug a little bit here, which I'm going to talk about for a little bit, which is what we call continuity of envelopes. So this is something that is necessary to prove the previous results. And so continuity of envelopes is a property simply of a pair XL that says that if phi 0 and phi 1 are two continuous PSH metrics on L, then the rooftop envelope is going to remain continuous. This is something that is very obvious in complex geometry. And if we draw a picture again, it's something that can be expected. We have two functions, and then we take their envelope is still continuous, even modulo the drawing errors, even if there's something singular. The envelope is going to be something like this. Oops. Okay. So I hope that you can grasp from these four pictures that this is something that is always going to hold in the case of convex functions and also in the case of PSH functions. But we do not know it in general in the non-Archimedean picture. So it's something that is also equivalent to many other important properties, such as, for example, the fact that the supremum of a family of PSH functions is PSH. But thankfully, we know that this conjecture holds in some nice cases, which we'll review. But what we expect in general is that we have continuity of envelopes for any variety X that is projective and normal over any non-Archimedean complete field, and with L ample. In fact, you can also ask for, well, yeah, for something like unibranch, which is a bit more technical condition, a bit more general, but yeah, projective normal is already good. And we know this to be true. For example, when X is projective normal, L is ample, as we said here, and the base field is C with the trivial absolute value, or the field of complex Laurent series, the work of Berman, Books, and Johnson. And really, this is what's important, right? Because for applications in complex geometry, these are the two fields that we're really almost always going to be looking at. So a more technical statement is that this is true in more generality over a field of equal characteristic 0, which has a discretely or true value, which has, sorry, a discrete or trivial value group, which includes these cases. Furthermore, by the work of Trillier, we know that this is true in general when X is a curve, and in equal characteristic P, we know that it's true in some cases, assuming resolution of singularities in characteristic P, which is another thing. But so what you should remember from this is that this is not a problem when we work over the trivially valued complex field or the field of Laurent series, which is really what's important for us. So going back a little bit to the proof. So for the continuity, we realize this envelope as a Legendre transform of another envelope. So we define this. So we lost the expression. I'm going to just write it again. Phi t equals the sub of PSH segments that are going to join phi0 and phi1. So we're going to realize this phi t as a Legendre transform. We first define this envelope at phi tau, which is the envelope of phi0 and phi1 minus tau. So if the endpoints are continuous, then by continuity of envelopes, this is also going to be continuous. Then so as I said, we show that this is realized as this Legendre transform, the supremum over all tau of t tau times this envelope. And in fact, the trick is to show that this supremum is taken over a compact set. And since we take a supremum of connect functions on a compact set, then this supremum is also going to be continuous. And then there are some other technical issues, but it works fine. The other thing that we use, so we have to use Legendre duality, which means that at some point we are left to consider infima of families of PSH function, of non-Archimedean PSH functions. And knowing that the infimum of a family of PSH functions remains PSH is something that is not really trivial. So in the complex case, sorry, even in the real case, you have f from say Rn to Rm, which is convex. You have what you call the infimum principle for marginals, or simply the Schellmann infimum principle, which says that the function that I'm going to say st here, the function that to t associates the infimum of S in Rm of f of st is also convex in T. So this is something that also works with the correct hypothesis for PSH functions. And it's a bit more difficult a priori to show that this is true in an Archimedean case, but in fact it works pretty nicely. You need the parameterization F to be convex NPL, essentially. So now, as you might see, we have two definitions. We have a definition of our distinguished geodesic as a, well, we do not know yet that is a geodesic. So we have the segment that is a supremum of PSH segments. We have this definition as a Legendre transform, but it is not at all obvious how to show that it is in fact geodesic for the D1 distance. So what we're going to do, as usual, we're going to simply treat the continuous case. This is all going to proceed nicely by approximation, because we have to, we can show that we can show that if phi k decreases to phi, phi 0k decreases to phi 0, phi 1k decreases to phi 1, then the distance of the phi k0, phi k1 converges to the distance of phi 0, phi 1. This is actually a bit of a involved computation, but it works. You also have to show that the envelopes are well behaved under taking decreasing limits in finite energy spaces, but this works. So if you like to use a fancy word, we can say that we use quantization techniques for a continuous case. This is really based on the work of Darvash and Rubinstein. You can also find some similarities with what Fong Sturm did with geodesic rays, for example. It also dates back to work of Benson and probability measures associated to the geodesics. So we're going to proceed with our so-called quantization. So we are going to take any tensor power of L. We're going to take the space of sections of KL, and any continuous PSH metric defines a subnorm on the space of sections of KL, which is defined as follows. So the notation can be a little bit confusing. So this is going to be a norm on H0KL. This is a section of H0KL. We define it to be the sub over X, actually Xn, if you prefer, of this quantity, which is simply, so you have S, which is a section of KL, so it's mapped from X to KL. And you have a metric phi, which you can see more or less. So K phi is going to be a metric on KL. And this quantity is simply equal to phi of K phi of S of X. So you can have an X here. So this is very much a subnorm, as I say. And so we're going for any k to define the subnorm nk of phi 0 and nk of phi 1, which are going to be norms on the space of sections of KL. Now, something that I'm just going to very briefly talk about is that the spaces of norms can be realized as what we call Euclidean buildings with a D2 sort of distance, and they have the cat zero property, which is something from metric space theory that simply says that they have a unique geodesic joining any 2 points, and this geodesic is also geodesic for a D1 type distance, distance on the space of norms, on the space of norms on H0KL, which is very closely related to the distance that we define on PSH metrics. So we can write it explicitly. If we take phi k and phi k prime to be norms on H0KL, we define the distance between them, the D1K distance. Again, if you like the fancy words, you can say this is the quantum distance between psi k and psi k prime. And this is going to be a sum of volumes this time. So the volume of phi k and the max of both norms plus the volume of psi k prime and the max of psi k prime. And so this volume can basically be understood as a sort of relative energy for norms. And in fact, you see that the expression is very, very close to the expression of a D1 distance on PSH metrics, except that we replace the energies with volumes, and we replace the these minimal envelopes with maxima, which makes sense because we have a nice correspondence between norms and metrics, which is order reversing. So anyway, oh, okay, this has to overlap. So now we're going to take this distinguished geodesic. So we say distinguished because it is unique for all the dp with p strictly larger than 1 on spaces of norms, but there are more geodesics for the D1 distance. But they're not very interesting and they're not very well behaved. But this is why we say distinguished. We have a very explicit expression for this geodesic in the preprint. And so we take this geodesic in the space of norms on sections of KL that joins the subnorm associated to phi 0 and the subnorm associated to phi 1. And something that you have to realize, so you might think, why do we not just take the subnorm associated to our segment phi t for all t? And in fact, this is not going to be geodesic at all. It's very poorly behaved. The idea is that the idea of quantization is this is not going to work, but it's going to work asymptotically in a sense as the powers of L go to infinity. And now the bulk of the proof, which I summarized in 4 equations. So we're going to go slowly over this. Basically, we're going to start with the end, especially this equality between these two terms. So the first really complicated part is to show that the limit of the distances between the endpoint norm, the endpoint subnorms are going to indeed quantize the distance between our metrics. This is building on some previous work of mine. And also in work of Buxbaum-Johnson in the trivially valued case. So we have that the limit of the distances between the endpoints are going to converge to the distance between the limit metrics. Now, if we go to the start, the problem is to also show that this approximation works for all t in both in geodesics between norms and in our candidate geodesic for phi t. And so once we have this, it's very easy. So you take S and T in 0, 1. You realize them as the distance of the limit of the D1K distances between the geodesics in degree K at time t and S, between the subnorms associated to phi 0 and phi 1. You use the geodesic equation, which then says that this is equal to absolute value of t minus s times the distance between the endpoints, which are psi 0k, psi 1k, which are exactly by definition nk phi 0 and nk phi 1. And then we use the quantization result again to show that this part converges, as I explained, to the distance between the PSH metrics. And the T minus S gets out of the limit, and so we're done. We have our geodesic equation if you take this. Okay, so thank you for your attention. This is where I'm going to stop.
Thank you very much for the nice talk. And now it's time for questions or any remarks.
So I have a question. So is the non-Archimedean K energy is convex in along your maximum geodesic ray?
We hope so, but we do not know this, unfortunately.
Yeah.
So this is a big question that we're all wondering if the K energy is convex along geodesics. It's even in the trivially valued case, it's very difficult to study. Without even talking about geodesics, it's just very poorly behaved. You have this article by Chile from 2020. I do not remember the title, but he makes some good progress on relating the trivially valued K energy and the complex K energy at the limit of geodesic ray. And even then, the results are only partial. And so for the convexity along non-Archimedean geodesics, we just do not know.
Yes, thanks. And is the non-Archimedean energy is affine in?
Oh, sorry. Yes. Yes. This is something that I forgot to mention. Yes, the energy is fine along geodesics.
Okay.
And this also characterizes the segment that we construct. Is the unique segment that satisfies this.
Thanks.
Some other questions?
I have probably one small question, Rémi. So can you say something? What do you use for your last slide about quantization? Do you have some sort of analog for non-Archimedean analog for Bergman kernel expansion or something like this? Or
yes, yes. Basically, yes. This is the result I was talking about here. Wait, let me go there. So the fact that this limit corresponds to this limit is a consequence of the fact that we can take so the volume of these norms. I'm going to call psi 0 bullet and psi 1 bullet, which are meant to psi 1 bullet, which are meant to represent the asymptotic norms. This is equal to the energy of the matrix by 0 phi 1. And you can, if you basically look at what we use for this, so we use this Fibonacci operator that turns the norm into a metric, and this theorem can be essentially seen as a Bergman kernel approximation. And the fundamental basis for this theorem, in the non-trivially valued case, this is basically the expansion of the determinant of cohomology. You realize this metric has models, and you take the first term in the expansion of determinant, and this gives the energy.
I see. Thank you.
Some other questions? All right, there seems to be no more questions. So thank you again, Rémi.
Okay, well, thank you again for the invitation. Bye-bye.
Bye-bye.
Bye.